In this video, I will be talking about a concept in topic 2.1, which is the equations of motion. So this video will be separated into four main parts, starting with an introduction, moving on to the process of deriving the silhouette equations, along with an example, and last but not least is a conclusion. So I will start with the introduction part. The equations of motion is also known as the silhouette equations. It contains four equations which relate five quantities together. These five quantities are S, which stands for displacement. Displacement is a vector and it's often confused with the concept of distance. It's important to know that the scalar distance refers to the total length of the path traveled, whereas the vector displacement refers to the changing position. So this graph shows the displacement and distance of the black object as it travels along the path. The distance traveled is shown in green. It's equal to the total length of the red path, which is 70 kilometers. However, the displacement is shown in blue, and it's varying as the object travels along the path, and the object's final displacement is only 14 kilometers in this case. The next two quantities are both velocities, and velocity refers to the rate of change of an object's position. It's equal to displacement over time. So here, u refers to initial velocity, which is the velocity at the start of the motion, and v is the final velocity, which is the velocity at the end of the motion. The next quantity is a, which stands for acceleration. Acceleration is the rate of change of an object's velocity. It's equal to delta v over delta t. All of these four quantities, s, u, v, and a, they are vectors, meaning that they contain a direction. And the fifth quantity is t, which stands for time. So the silhouette equations can only be used in the case of constant acceleration, including zero acceleration, and when three of the quantities are already given or can be figured out. Knowing these five quantities and the relationship between them, we can derive the four equations of motion. So the first equation can actually be derived from the definition of acceleration. We know that a is equal to delta v over delta t. By rearranging the equation, we can get v is equal to u plus at, and this is our first silhouette equation. The other three silhouette equations need to be derived with the assistance of motion graphs. So here is a motion graph in the case of a constant velocity. So we can see that the area under the graph is equal to v times t, which is equal to displacement. So from this graph, we know that the area on the velocity time graph is always equal to the object's displacement. So now we can consider a case where v is changing and acceleration is constant. So here we can see that the area under the velocity time graph is a trapezoid. We can directly calculate the area of the trapezoid using the equation the top plus bottom times height divided by 2. Because the area is the displacement, we can get the relationship that S is equal to 1/2 of u plus v times t, and this is exactly our second silhouette equation. We can also calculate the area by breaking down the trapezoid into a rectangle and a triangle. So if we do it this way, the area will be equal to S equals to ut plus 1/2 of v minus u times t. Because we know that v is equal to u plus at from the first silhouette equation, we can substitute in this relationship and rearrange the equation. Then we will get S is equal to ut plus 1/2 of at squared, and this is our third silhouette equation. The last silhouette equation can be derived by substituting in the first equation into the second equation, and the deriving process is a bit time consuming, so I won't include it here. But the last silhouette equation is S is equal to v squared minus u squared divided by 2a, and this particular equation is very useful when the time of the motion is unknown. Knowing these four silhouette equations, we can move on to an example. So let's consider a case where a car is traveling on a highway at a speed of 20 meters per second, and the car's engine suddenly stops working, and the car decelerates at a rate of 5 meters per square second. So the question is, how long will it take the car to stop completely? So when approaching a problem like this, we should first list out the information we already know. In this case, we already know u, v, and a. They are all given in the question, and we want to solve for t. So S, displacement, is not really important in this case. If we only care about u, v, a, and t, we can apply the first Suvat equation, which states that v is equal to u plus at. And when we substitute in the values we know, we can solve for t and get that t is equal to 4 seconds, meaning that it will take the car 4 seconds before it comes to rest completely. If we slightly modify the question, we can also ask how far will the car travel before it comes to a complete stop. In this case, we don't really care about t, we only want s, u, v, and a. And u, v, and a are already given in the previous question. So we can apply the fourth Suvat equation, which states that s is equal to v squared minus u squared divided by 2a. Then we can solve for s and get that s is equal to 40 meters, meaning that the car will travel for 40 meters before it comes to a complete stop. And the last part is a conclusion. So the equations of motion contain 4 equations which relate 5 quantities together. They can only be used in the case of constant acceleration, and when 3 of the quantities are already given or can be figured out. So in more complicated case, we might need to break down the motions into different parts and apply the Suvat equations individually, and there are many potential extensions to the Suvat equations. However, it's very important to note that the Suvat equations cannot be used in the case of non-uniform acceleration. And this is the end of the video. Thank you for watching. Here is the reference list.